Every second, modern corporations generate an almost incomprehensible volume of data. Millions of rows of transaction logs and user clicks are recorded every hour, filling server racks with a constant stream of raw values. When you are dealing with petabytes of information spread across hundreds of variables, standard spreadsheet software fails. A human analyst looking at these tables would see a wall of text that is effectively unreadable. Data mining solves this bottleneck. It is the computer science process designed to scan these massive datasets and automatically extract patterns that a human can actually interpret. But data mining isn't a single tool. In practice, the field is split into two distinct branches based on what you're trying to achieve: describing the present or forecasting the future. Because raw data has no inherent value without a specific objective, analysts must choose a path. You can use algorithms to discover what is currently hidden in your system, or use them to predict what will happen next. Describing the present requires unsupervised learning. These descriptive algorithms explore existing data to reveal underlying structures and relationships without looking for a predefined target outcome. A primary example is clustering. This method groups a massive collection of unlabeled data items together based strictly on their mathematical similarity. Algorithms like k-means calculate mathematical distance between data coordinates, maximizing similarity within a group while keeping different groups distinct. In retail, this automatically segments a chaotic database into actionable profiles, like budget buyers or premium shoppers. Another descriptive method is association rule mining. Instead of grouping people, it evaluates transactional data to find concurrent purchasing patterns using probability metrics. This is the engine behind market basket analysis. The algorithm calculates the frequency of items co-occurring, discovering, for instance, that a customer buying a laptop has a high statistical probability of purchasing a wireless mouse at the same time. By extracting these structural affinities, businesses can optimize their physical store layouts and current marketing operations based on how their customers are already behaving. If the goal shifts to forecasting the future, you need predictive algorithms. These operate on supervised learning, meaning they are built with a specific, predefined target variable in mind. The system analyzes historical datasets where the outcomes are already known. It learns the boundaries and patterns of those results, building a model capable of forecasting outcomes for new records as they arrive. One of the main predictive methods is classification. This algorithm maps incoming data instances into distinct, predefined categories. By learning from past applications, a decision tree builds boundaries to categorize new inputs. A bank uses this to instantly sort applicants into approved or rejected. That same logic applies to healthcare. By analyzing vital signs, classification models predict if a patient is high or low risk. When the desired target isn't a category, but a continuous numerical value, we use a different predictive method called regression. This graph shows how regression models the relationship between variables. By fitting a line that minimizes the error distances across historical data, the algorithm can generate precise estimates, like predicting a property's future real estate value based on its size. By feeding the algorithm historical answers, the math shifts from exploring current structures to calculating the probability of a specific future outcome. Conceptually, you can think of descriptive algorithms as a map and predictive algorithms as a compass. Descriptive models take the wilderness of raw data and reveal the hidden terrain. They show you the affinities, the segments, and the anomalies that exist right now. Predictive models leverage the knowledge of that mapped past to point toward highly probable future results. Modern organizations deploy both in tandem. This is how hospitals optimize oncology treatment paths and how financial networks identify and neutralize anomalous red data clusters in the form of credit card fraud. Modern data mining allows organizations to move beyond audit-trailed histories. By combining these two methods, they can actively engineer their future trajectory.